Alright guys, so we're going to be working on a global B E99 ECU, and unfortunately we're going to have to go ahead and split the file in order to get our disassembly to go correctly. So I'll show you guys how to do that, and it'll just kind of add an additional element when you're creating a map pack in WinOLS in order to get all the addressing to align. So alright, so I've already created the project here. To create a project, you just say new project, you select the repository you want it to go to, and you go from there. We're going to go ahead and import the file again. Okay, and we're going to type in PowerPC, and it's going to be this Power ISA 3 Big Endian with VLE EVX. Alright, we do not want to analyze. So the first thing to take note of is this AA55. We're going to go ahead and search the opposite of this. So we're going to search 55AA and then some F's on the end of that and do a search next. Not found. Search next. Okay. Alright, so this is it right here. So this is the end of the operating system file, and right here is where, like, your calibration area, the best I can tell. This is your calibration area past this point. So this is at 6BF77. So we're going to go ahead and click on this, and we're going to say split, and we're going to say end address of what we just copied there, and hit OK. We do want to take a minute to rename these. 0 RAM split. Alright, so this one, how do we rename this? There we go. We're going to call this OS, the operating system, and we're going to call this calibration. Okay. Now we're going to move both of them. So this operating system lives at 94,000, well, 940,000 rather. This one here, it actually lives at 841234 zeros. Alright, so now we'll see that there is a difference. We need to create a binary. So there's a difference between these two values right here. Alright, so now we need to create a filler section, because this one ends at FFBF and this one starts at well, 4 and then 4 zeros. Alright, so we're going to take our calculator and we're going to take, whoops, this value in hex rather minus this value 41, so it's going to be actually 40 long because we don't want it to end at 94,000. So we're going to create a block. Block name is going to be filler, and its start address is going to be 93FFCO. 93FFCO, yep. And then it's going to be 40 long. We do want to check this box right here that fills it with bytes, and we're going to fill it with Fs. Yep. Okay, we're good there. So now we need to go ahead and hit File, and we're going to export, and it is going to be raw bytes. Okay, and that will allow us to import that file into WinOLS. Okay, so next we're going to go ahead and we're going to search, and it's going to be a string. And the value we're going to search are Ds. Well, they're actually capital Ds. This is something that I have seen frequently in PPC or MPC files. Sorry, next. So at this first one right here, we're going to go ahead and hit F12. Double click on that, and that brings us to our registers. So one thing I do like to do is keep a notepad++ going of these registers, or of the project rather. So we're going to copy this, throw it in here, and then is what this instruction is doing is the ELIS is loading 4002 into the upper 4 bytes of R13, and then 5F40 is loaded into the lower bytes of this. Okay, so that is what the address assignment ends up being. Okay, you'll notice that R3 does some stuff right here and then loads into this instruction, or whatever this is doing. We're not going to set R3 at this time. I don't think it will need to get set, but it is something to keep in mind if we come across a function that has like in R3 and then adds or subtracts a hex value from that, then maybe we need to take another look at R3. But regardless, we're going to go ahead and assign these values to our registers. We can... Oh yeah, it stopped. Okay. So go ahead and copy that value. Put your click on the register you want to set, Control A, Control R, and then you set it to that value. We're going to go ahead and Control A, Control R. Control A, Control R. And so on until we're finished. Go ahead and get rid of that for now. So at this point, we would like to set up our memory addressing, our RAM. And I believe that RAM on this is going to be 412312334, and then a length of, is it going to be FFFFF? We'll double check real quick. That should be it. I think that's plenty long. I think that's longer than it needs to be, but that should be fine. Okay, real quick, we want to set our calibration area to just be read. You can debate whether you want to be execute or not, but there shouldn't be any code in our calibration area, so it shouldn't be executable. But maybe there's going to be small segments here and there that can happen, so we might want to check that back. Filler is nothing. We might leave it read just in case something has a pointer there, but it shouldn't have any pointers there. And then the operating system is going to be read and execute, but not write. The RAM is going to be read and write, and then if you can find some data sheets on this processor, you would also be able to, get a better idea of exactly how large the RAM is, and then the input and output, the I/O area, would be checked as volatile. But just the I/O area would be volatile. Okay, this looks good right here. We're going to go ahead and select the calibration area. Oh, but we split. Here we go. Sorry, not the calibration, the OS. So we're going to come to right here, and we're going to say select, mark selection, and then we're going to go to our RAM address right there, and then scroll up to here. This is the end of our OS, and we're going to hit select. Ooh, bummer. Create selection. Oh, there we go. There we go. So then we're going to hit F12, or if that doesn't work, we're going to right click, which it is working. And we're going to set the, say, disassemble PPC VLE. All right, let's go find where we exported that binary to. All right, so we're going to say new project. And we're going to go ahead and grab that binary that we compiled. We're just going to say E99 video Okay, so there's some things to take note of really quick. So first off, we need to get our offset the same as what we see in Ghidra. And when we split the Ghidra file into two pieces and made our OOS and our calibration area, we set our calibration area to 84,000. So we're going to go ahead and hit the question mark here, and we're going to say edit. And we're going to set our display offset to 841234 and hit OK. You see how it doesn't do anything right here? Click the question mark and just wait for a second. And there it set it. Okay. So now we're good there. One thing to take note of, the way the file was given to me in a pre-compiled state, the operating system was on the front end of it. So if you import this file again without first splitting it and then recompiling it, this map pack is not going to work for this. Even if you set the display offset like I've set it, because WinOLS sets its map pack based on the offset of the beginning of the file. You know, it starts counting from here. So if you have the OS on the front of it, it's going to start counting from the beginning of the OS, and the map pack is not going to work. So you guys are going to have to kind of settle that how you want to. You can set the split and recompiled version next to the version that you have, and then convert your maps from one to the other. That would be fine, but regardless, there's going to be some messing around there. Let's jump back into Ghidra. We're still decompiling. Let's check WinOLS to see if my... Yeah. Okay, we're good here. Oh, wait. Oh, it didn't import the maps. Okay, so this might be a good example. So we're going to set these two files next to each other and do a compare. We need to open this, I guess. Yep, compare those to each other. Okay, and we're just going to double or right click here, view in hex dump. We're going to copy this map, and we're going to hit that right there. One found, and there you go. So then while we're here, we're just going to click this, and it's going to copy the selected map into our new project. Okay, at this point we can close down this older project. Okay, and close this, and now we have imported the map into our recompiled binary. Let's copy this address right here and throw it into Ghidra and see if we have an XREF for it, and we do. Okay. Okay, and this looks good so far. So let's start digging into the mass airflow meter. Whoops. So this is going to be the map data, and this is going to be the x-axis. So we already have that copied. We'll go back to it, and we're going to highlight or copy this, hit L. Notice that there's not a name right there. I'm going to show you something. Okay, the name changes right here. If you click on one of these and then try to change it there, it pulls up with the name populated inside of it. Okay, copy that address. G, paste. We have xrefs. We're going to say math axis in hertz. Once it's been named, then it does populate in this first view. I don't know why. Okay, so there we have these. So you can see math hertz right here is in this string code. Right here we have a value of 4. Right here we have a value of 60. This is a RAM address. We can only assume that it's hertz. We click on this and we see param 1 times 4 equals param 1. So right off the bat, the RAM address gets multiplied by 4 and then gets pushed through. Arguably, in order to see what the value actually is, we know that we're multiplying this by 4, the RAM address by 4, to then be able to use the data from this axis. So that would be the same as dividing the data in ROM by 4. Okay, so we're going to jump into WinOLS, and we'll see that we've already, somebody sent me this map, which was cool. So when we look at the x-axis, we see that yes, the axis is being divided by 4, so this is the correct scaled value. Okay. So looking back into Ghidra again, we'll see that this value right here is 60, right? And we can reverse engineer this, but what it's doing is this is 16-bit high-low. So this is considered 0, and then 1, and then 2, and 3, and 4, and so on. So this value 60 here is telling us that it's actually 61 long. So if you go into properties, the mass airflow sensor function or scalar, whatever you want to call it, calibration map, is going to be 61 long, which that's good. Okay, so then the map data, this is map data right here. UVAR1 is the output of this, line of code with this function. We're gonna go ahead and name this function 2D X axis. And this might be used for 3D maps, this might be used for Y axis, but we know right now it's being used as 2D X axis. So then our math data, again 60 long, and we have a 0.078. Let's look at this function. Let's look at param4. Okay. We'd have to get a little bit heavier into it. This is a bit mask, but it looks to me like param4 is just multiplying whatever data we collect prior to returning it to whatever's calling that function, and in this case it's being returned and written to this RAM address right here. Alright, so let's go ahead and grab, so this 0.0078 in WinOLS is going to be what we multiply by the map data, which you see right here, which he already did, and this is scaled properly, so good job on that. But while we're looking at maps, I've been having some unique, indiscrepancies with the axis data of this map. So we're going to copy this address, and hopefully we got it this time. So while we're here, we're just going to say, well, no, I'll show you something else actually. We're going to copy this. We're going to click on this function. Sometimes these functions are absolutely massive, so you can hit Control Find after you click in here somewhere, and you can paste this and hit Next, and there you have it right there. That can save a tremendous amount of time. So we're going to say, map in question. Okay, and we're going to call this a 3D function or 3D map. Too long. I don't like long names. On these ones, arguably you can get rid of this address. You don't really need that. Okay, we're 6 by 6, which is 7 by 7. So we're going to go ahead and hit K. Double click. And we're going to say 7 by 7. And then we're going to hit Auto to get this bar to populate correctly. Okay, that looks good. If we had this set up by the wrong length, it would be really distinct. If you do a 6 by 6, you can just see that is messed up. So 7 by 7 is correct. Okay, and now in this case, we're going to be X, Y, and Z. So let's chase down the X axis and see if we have. We do. Perfect. And the Y axis. And we do. Oh, but that's for the wrong one. Hang on, where were we? Map. Map. There. Yep. Reads and write. And reads and write. Okay, perfect. BEO is right, so we're going to hit this read. We're looking for BEO. We could have copied it, but we did not. BEO, 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 right here. Okay, perfect. So here's our x-axis right here. Oh, and here's y, I believe, this one right underneath it. But we're going to grab this address right here. We're going to copy it. We're going to throw it into WinOLS right here as EEPROM paste. Okay, 32-bit float looks good at first glance. We'll see. 6 long and no multiplication. So that would make sense if it's 32-bit float. If it wasn't float, we'd have an addition. So we can call this, notice how they're both the same, 9C5BC. So we're not going to say X or Y, we're just going to say axis. So that was X and this is Y. So if you ask me how do I know one's X and one's Y, and the answer is because I went and found a map that wasn't 6x6, it was 6x7, and then I reverse engineered to the addressing and I found that one scalar, if one's 7 long and one's 6 long and you put the wrong one in the wrong place, a value ends up dropping off and looking really funny. So that's how I know we are XYZ from right to left, which is not. Typically, it's X, Y, Z from left to right. All right, typically you would spend some time and name all of these. Additionally, if you know what this maps, like this looks like RPM. I'm just going to say that's probably RPM. So that is Y. So we can go ahead and name this RAM address right here RPM. I'm like 90% sure. RPM equals RPM, which is this function right here. And it looks like the decimal, it looks like in order to get this afloat, you multiply it by 0.125. Oh, there's more math going on. Loads of math. Well, it doesn't really matter an awful lot. I don't care, honestly, if it is RPM or not. My point is, when you enter your maps in, FR9 float equals if RPM is more than yeah, I'm pretty sure this is RPM, but regardless, if you know what your X and Y data is of a map, this is how you end up doing it. I would then take RPM and I'd paste this as RPM, and then I would paste this as RPM variant or raw or whatever you want to do. And then this again is going to be another variant of RPM. All of these need to get RPM named on them, if this is indeed an RPM axis. I feel like we've covered maps good enough. Between the math scalar and seeing its multiplication and this axis for float axes, I think we're pretty good there. Let's jump back over to our math. I realize we're kind of skipping around a little bit. I apologize. So we're going to go ahead and hit L, and we're going to call this. Okay, and we're going to click on our data here. COO. I'm a little curious why it's not showing it's being written to. We might have to analyze. I think we're going to have to analyze once the disassembly is done. Okay, good. So you'll notice how this is not being written to. I think it is noteworthy. We should take notes right now because I think we're going to have an issue here in a minute. But we're going to go ahead and hit analyze. And we're going to take a small break as this does its analysis. Disassembly and analysis are two different things. So we'll go ahead and pause the video. All right, so we've completed analysis. There are a couple things that I want to check really quick. First, take note that we now have these two writes to 52CCO. This is a little weird to me. This looks like it's a second math table. It was suggested that some of these vehicles with E99 ECUs has two mass airflow sensors, so maybe it's mass airflow meter 1 and mass airflow meter 2, and both of them get written to this address. That could be. Also take note that there are no reads whatsoever from this address right here. Alright, so one thing I did do is I went ahead and searched this value right here. So this is how we calculate 52CCO. We subtract 5C40 from R18, the register that we have set, and then we load that into R3. So I did search this value, found a couple instances of it, but it never again was used to create, this CCO. So we are gonna name this math. I think that you should spend some time, if you want to figure out your math flow RAM address, you need to spend some time looking at the assembly code here. I don't think the decompiled code is displaying it correctly, and you'll have some time into reverse engineering this, but that'll be on you guys to do yourself. So let's take a quick look at math hertz. So we'll go ahead and label this, because this is our math hertz RAM address. We're going to take it and we're going to click on what's reading it. Okay, we see that it's being compared to these data points. Okay, these are definitely, this is a big deal. Where are these being called from? Here it is. If this is setting DTCs for like mass airflow hertz high and mass airflow hertz low, this 1500 right here is being called from here. And then this is called from here. So we can go ahead and throw these addresses. Let's see. Hit A, paste right there. Yeah, those are them. So we're going to go ahead and double click there and hit 2. And we're going to call this math hertz max min. Definitely spend more time on this. This may not be the true max min. We do know that based on these thresholds, something happens. Okay, and what does happen? So this is a counter. So if RAM address right here starts out as 0 and this condition happens, it will be incremented by 1. If it's 2, it hits 3. If it's 3, it hits 4. That's if this statement is true, if math hertz is low. So we're gonna, I think this is a fault. We're just gonna say math HTZ low counter. Okay, and then if math is high, again a counter. Math hertz high counter. Okay, and then we also want to name these while we're here, and we're just going to say math fault might be a strong term for this, but that's what we're going to call it. Oh, we should be saying hertz fault, but whatever. Okay, let's highlight these real quick. Sets to 1. Here's more. So if this data equals, does anything, nothing writes to that in this function. Okay, so math hertz fault equals 0 if it doesn't return. Okay, if math hertz fault equals 0, this is this. then set it to 1 and return. But then this statement won't be true anymore once it's set to 1, and then it'll run its checks. So that is something worth looking at. You'll notice that these are set to 1, 2, or 3, and then 1 and 0 and 1. Again, fault might be a strong term for this, but we're in the stages of throwing names at stuff. And maybe I should say might be fault, but regardless. You'll have plenty of hours to come back to this multiple times. So we're going to say math, hertz, max, min. Okay, and then the counter is definitely what we're looking at. So here's another function that writes to it. Math hertz counter is set to 0. Based on this condition, and this condition being this is less than whatever the heck that means. But we do see that math hertz less than 400. Math hertz, where's this 400 coming from? It'll be an address like this right here. Yeah, that's it. That'll be 400 in decimal, I'm fairly certain. Okay, so if the counter is less than 400 then this value equals the counter. If it's less than the counter, it equals the counter. It's an odd statement. If this is not true, if it's not less than, so it's more than, so it would be good to know what other functions write a 0. Okay, so this is equal to 0, like this is a key on reset or a DTC reset of some sort. So its normal state is 0, unless there's a portion of this. Maybe there's a third thing that writes to it. We should check that. So we're going to hit xrefs, and oh, there is. So there's one write, there's two writes. Oh, equals what? Reset to 0. Here it is. So if data is other than 0, and then if this data is equal to 1, else return. And this one we're looking at is 9C. So if it's other than 0. Else, if, else. Yeah, this is for you, man. You can spend some time going down this rabbit hole if you want to. I would like to mention that I find it highly likely that these functions right here are DTCs. So like this being less 2 might reset this DTC at 0x45 maybe. But we're just going to say might be DTC reset. And we're going to say might be DTC set. $918 times seems right to me. And then the set is used 937 times. Data at 01s, that's pretty common to see. Param 1, see how param 1, which is that, hex value we mentioned, is being pulled into all these different functions. So you'll need to spend some time on every single last one of these functions, and is what you're trying to track it to. OX times OX 290, 656. So what you're going to be looking for is a case in which it's using, you want to track this to your hex table, DTC hex table, and it might require you tracking a value being written to a RAM address and then, or read from a RAM address. And then you might be able to track your DTC hex table 0006, 05, 06, 05, 06, 05. It's likely that you'll be able to track a DTC hex table through these functions. Figure out the offset that it's writing to a RAM address, and then see how this is setting that same RAM address or another with the same offset. One thing you can do, head over to these max and minimum values and just set this at, like, 2000 and see if you get a DTC set on your vehicle after driving it. All right, we're going to go ahead and jump into some possible flex fuel things that there were some questions about. So the question was asked about whether some bytes in a certain address would enable flex fuel. And I was given the address, and I've been looking into it. One thing that's unfortunate about Ghidra is it will look at the value of some of the pointers that it has, like to the flex fuel bytes, and it will go ahead and just disable the decompiled view of the rest of the function. So in order to reverse engineer, you have to then click on this write ability right here to the calibration area. So now that we've done that, then it will check if this is equal to 0 or not, right? These flex bytes. That's kind of frustrating. It annoys me a bit. But these are some techniques. If you track a xref to a function, you get there and this is what you see, just returns 0. Well, you might need to click this write to see if there's actual, I mean, clearly there's a function here. There's code, right? Why can't we see it? Well, I guess that's why. I don't know why Ghidra does it. Don't love it. I, in fact, dislike it. Probably a way to turn that off. But regardless, this function checks to see if it is equal to 0. And then if it is, it continues on and does all of this. If you want to track some of this stuff down, I would label all of these, might be related to flex or related to flex or whatnot. Okay, we're going to go ahead and hit another xref here. Okay, now there is something going on here. So here's our flex bytes. Our flex bytes are being loaded into R7. If flex bytes equals 0, do this, else. Alright guys, so this is pretty annoying. So you'll notice this is the function that we're looking at reverse engineering while the flex bytes are set to 0. But then if we patch this data to 1 and hit enter, suddenly you can see all these bytes also, or values. So this is kind of significant. I didn't know Ghidra was doing this. This could lead to, some pretty bad disassembly if you're reverse engineering one version of a calibration file, but in the next version, suddenly some bytes are enabled and you haven't even gone through these additional functions. That's not cool. Okay, I think, so this is the flex byte that we're comparing. So I think it would be important to label this flex CMP compare question mark. Okay, and then take note of what's going on right here. 361 and 1239, 720. So if it's more or less than, it can also equal this RAM address. So this RAM address will equal the outcome of this function, or it will equal this RAM address right here. and then is compared above and below these two decimal values. I would label all of these, you know, flex look at me or look at me, and I would dedicate some time. If you want to understand reverse engineering this, you know, flex fuel system, you need to end up tracking this variable to SAE PIDs, to SAE DTCs, or to an axis of a map that then you can infer what this is. You know, maybe it's lambda, maybe it's ethanol content, maybe it has an effect on your spark tables, right? Need to spend some time on that. I know I'm not thoroughly explaining how this function works, or any of these functions rather, but it's not something a guy can do in, you know, a matter of a few hours. Like you have to reverse engineer the ECU with all known parameters you have, maps or PIDs or SAE DTCs, and then move on from there. Okay, here's our flex bit, I'm sure again. We'll go ahead and search flex bytes. Okay, and we're going to see what this function does. Change this to a 0. Sure enough, it changes. And I think it was this. Was that the byte that changed? Man, I'm not seeing which one's changing. Okay, so what we did here is we just checked this to write to try to keep the function from changing so much. And then we're going to hit Control Z to change back to 1. And Control Shift Z. I'm not seeing anything change, guys. Am I blind? Oh, it might be an offset. It might be one of the other bytes in this function. That could totally be it. Yeah, that could be it. Okay. Well, regardless, that's set back to the proper. So I would go ahead and start tracking down, like this RAM address right here is probably going to be used in the x-axis of a map. Yeah, you're going to have to start just tracking these throughout the ECU and try to find the closest map, I guess. The disassembly does look good now. We look pretty dialed in. I'm pretty stoked about that. It took a minute. I was finding a lot of bugs. Flex compare. So it would be good to see what writes to this flex compare. Oh, it writes to it right here, actually. Is equal to 1. And the other option is setting it to 0. So like key on reset maybe. Okay, and then it sets it to 0. So then is there another function that reads this byte? There's not. Okay, just the first one. So based on these datas, this will be written to. If and this is more than that, this will be written to. Okay. If data equals 3 equals param 1. So that's not insignificant. So you might take this and search and see if anything comes up. Okay, no match is found. And the same thing here. Okay, no match is found. So what we're looking for is maybe a pointer that points to this function that would set its byte. So what we will do is we'll scroll to the top of this array of pointers. Yeah, this could be significant. So you could spend some time looking at these XREFs And you might find that based on these xrefs, these different functions are getting called by a indirect addressing. Let's check out this value. We're going to say while we're here, we're just going to copy this and say number 2. And then it only gets to write if it's below or above. This is the default. So 720 is the default if it's outside of its threshold. And this is the value if it's within its threshold. Okay, and we're going to call this a variant. It would be interesting, I don't know, you need to track this to an AFR table or something like that ultimately. Flex fuel value proper, flex fuel related, and then, all right, flex fuel proper, uvar1, uvar1, uvar1 equals this. It's other than 0. uvar5 equals that, but it could take on this value right here instead based on this if statement. uvar5. It's not the same function we were just in though. Nothing there. Oh, we're getting close. All right, something's going on here and it's not showing us. Because this value isn't being produced over here. I think it could be like one of these axes. Yeah, this is being used for 2D scalars now. Here's a stack of tables. This is what it's going to look like. You're just going to have to start tracking. If you want to know about this flex fuel stuff, you're going to have to start tracking the values found in those 3 functions that reference that set of bytes. And you're going to need to figure out what tables they play a role in, and eventually you'll have a good idea if it's affecting your fuel strategy and how exactly. That'll pretty much wrap it up for the videos. I may go deeper into this at some point and produce some more videos on it, or I might just let this one sit. If you have any specific questions, go ahead and send me an email or whatever. So, alrighty.